Hi everyone, my name is Justin Lubin, and I'm here to talk about how statically typed functional programmers write code. There are many different statically typed functional programming languages, including Haskell, OCaml, SML, Elm, F#, and many more. Each of these languages have their own set of distinguishing features, but they all share a common set of features and norms that differentiates them from other classes of languages, including expressive type systems, strong static guarantees, and an emphasis on small and reusable functions free of side effects. The question that we set out to answer is, how do the affordances and community norms of statically typed functional programming affect the way programmers write code? Now, why should we even care? Well, such a study could give a foundation for useful and usable tooling for these languages. It could enable more ergonomic language design going forward. It could provide eased on-ramps into these languages' communities by introducing newcomers to how programs tend to actually be constructed in practice. And lastly, it could serve as a template for studies of other understudied programmer audiences. And this last one is one I'd like to emphasize a bit in this talk. I really encourage you to think about how the methodology I'm about to describe could be applied to a group of programmers that you especially care about. However, before diving into the methodology of my study, I need to give a little bit of background. Our goal is to develop a theory of how statically typed functional programmers write code. To do so, we turn to something called the grounded theory method, which is an approach to theory development with a long history in the social sciences that emphasizes an iterative cycle of data collection, data interpretation, and theory development. At a high level, it operates as follows. First, the researcher collects data. Then, as the researcher collects data, they tag it with increasingly abstract categories that are, ideally, the simplest possible explanation for the data at hand. As more data accumulates, this simplest possible explanation will grow more nuanced when unexpected or surprising new data challenges the developing theory. This process finishes when the theory reliably accounts for the data being collected and no more surprises are found. Now, with that background in mind, let's take a look at an overview of our particular methodology for this study. We started with recorded observation of statically typed functional programmers, which provided the raw data for the tagging analysis that I described earlier. This analysis provided increasingly nuanced topics to explore in the observational process, leading us to hunt for data samples that tested and refined the theory at its weakest points. This process is called the grounded theory method, and resulted in a grounded theory of how statically typed functional programmers write code, the first and main contribution of our work. To gain increased confidence in this theory, we approached the topic with a second, contrasting methodology. We derived a set of testable hypotheses from the grounded theory we developed and performed a quantitative experimental evaluation of them, resulting in statistical evidence that gave us increased confidence in our theory. This quantitative experimental validation of our qualitative theory is our second contribution and provides a mixed method lens into the question of how statically typed functional programmers write code. Finally, we synthesized the qualitative information from the grounded theory and the quantitative information from the experimental evaluation into our third contribution, implications and takeaways for designers of statically typed functional programming languages and tools. Like I mentioned earlier, this process is entirely generalizable to other classes of understudied programmers, and we'd love to see more qualitatively driven mixed methods approaches to understanding how users interact with programming languages, tools, and environments. So, let's take a look at the first part of this approach, the grounded theory method. We did a grounded theory analysis of 15 live, statically typed functional programming sessions over Zoom, where participants first completed some functional programming tasks that we assigned in a statically typed functional programming language of their choice, then engaged in a semi-structured interview about their experiences, both in the study and prior to it. In addition, we analyzed 15 sessions drawn from statically typed functional programming live streams on the websites YouTube and Twitch, for a total of 30 statically typed functional programming sessions. Our goal in including the live stream sessions was to diversify the programming tasks that we observed, with the hope of increasing the ecological validity of our findings. So, without further ado, how do statically typed functional programmers write code? Well, our theory comprises four main categories: type construction, focusing techniques, hierarchical and opportunistic programming, and reasoning and intent. At a high level, our answer to the question of how statically typed functional programmers write code is this. They start by iteratively constructing types to model their problem domain and encode design decisions. They leverage types to help themselves focus by relying on the compiler as an assistant and using these types to help plan and decompose their tasks. When faced with a difficult or unknown problem domain, they complement this systematic style of programming with an exploratory one, the details of which are highly varied. And lastly, no matter the style of programming, they reason about code differently and express their authorship intent in diverse ways, not all via valid code. While I'd love to talk about all 4 of these categories in this video, I really only have time for one example from one of these categories. So let's take a look at this second category here, focusing techniques. One interesting way participants focused on tasks at hand was relying on their compiler not just for corrective feedback, but as a guiding assistant. For many participants, error messages from their compiler were not just an obstacle to getting their code running, but actually served to direct their implementation. One common instance of this was using compiler error messages as an auto-updating to-do list, or what participants refer to as following the errors. The way this strategy works is as follows. First, the programmer comes up with an idea about a change they want to make to their program. They express their intent to complete this change by modifying just a small part of the program, thereafter immediately running their compiler on the code, despite being fully aware that the code will not compile. From there, the compiler presents the programmer with a list of errors that can be treated as subtasks to complete the transformation. The programmer can just follow the errors. As one participant put it broke a lot of stuff, but it was super nice because I made the change and the type checker told me, this no longer type checks. Here's all the places where it goes wrong. And I can just go through and fix all the type errors, and that essentially is doing the change. Alright, so that was a sample of the qualitative portion of this project. Now let's take a look at the quantitative portion. So we have this idea from our grounded theory of following the errors. How do we take this multifaceted concept and transfer it to the cold and blunt world of quantitative studies? Well, one way to do so is to operationalize it as a testable hypothesis. Here's how we did that. Hypothesis. Statically typed functional programmers run their compilers on code they know will not compile. It's impossible to capture all the nuances of a qualitative study in a quantitative one, but this hypothesis will at least tell us if our theory is on the right track. Indeed, if our theory is correct, then the outcome of our quantitative experiments should be entirely unsurprising, as they will support the conclusions we already discovered in more detail in the qualitative analysis. And that brings us to our experimental validation. Here's how we tested that hypothesis. First, we assigned each of 12 participants the same task in the same language, Haskell in this case. Then, each time they were about to compile, we had them briefly let the investigator know which of the following statements best applied. You know the code will compile. You believe the code will probably compile. You believe the code will probably not compile. And you know the code will not compile. We can plot participants' responses as a timeline and note the number of times each participant responded with a will not or probably will not belief. If we take a look at participant 12 here, we can see that they mostly responded with positive beliefs, the black markers, but there were 2 times in the middle, the orange crosses, that they were confident that their code would not compile. Overall, 50% of the participants reported at least one instance of believing that their code would not compile right before they ran their compiler. We can use a Wilson confidence interval to make some predictions about what the population of Haskell programmers would do in this situation, and we see that our confidence interval ranges from 25% to 75% at the 95% confidence level. This means that we have confidence that at least 25% of the population will behave in this way. We can also relax our belief criterion to also include all the times that the participants indicated that their code probably will not compile. In other words, anytime the participants expressed a negative belief of any kind about their code's ability to be compiled. In this case, we see that 75% of the participants had a negative belief, and we get a Wilson confidence interval of 47% to 91% at the 95% confidence level, giving us confidence that at least 47% of the population will behave in this way. With these results, I feel pretty comfortable accepting our hypothesis that statically typed functional programmers run their compilers on code they know will not compile. But I do encourage you to take a look at our paper for details and determine for yourself the extent to which our claims may or may not generalize to real-world statically typed functional programming beyond our specific tasks that we assigned in Haskell. So, that was a taste of our experimental validation. Let's finally turn to the implications and takeaways that our work has for designers of statically typed functional programming languages and tools. Our grounded theory of following the errors and our experimental validation that statically typed functional programmers run their compilers on code they know will not compile have three immediate implications. First, and somewhat counterintuitively, statically typed functional programmers are already using their compilers for reasons other than producing a compiled program. That's interesting in and of itself, and suggests that it's worth considering viewing the compiler as more than just a translator from one language to another. Second, statically typed functional programmers often want insights from automated tooling before their programs are compilable. This means that automated tooling should do its best to extract as much information as possible from code that does not compile. And third, compiler error messages may not really be caused by programmer errors at all, but by deliberate behavior specifically intended to elicit compiler feedback. This means that maybe we should reimagine compiler feedback as occasionally being directive in nature rather than strictly corrective. So, that is partly how statically typed functional programmers write code. Here are some reasons we might care, an overview of the mixed methods approach that we took for this project, and a high-level overview of the resulting grounded theory. You can find me on Twitter at jplubin, and you can find the slides for this talk on my website, jlubin.net. Lastly, I want to take a moment to thank the anonymous participants of our studies for making this research possible, as well as the anonymous OOPSLA 2021 reviewers and the Chi SRC 2020 judges for their feedback. I'd also like to thank Ravi Chugh at the University of Chicago for the great conversations that led to the development of some of the questions addressed by this project. Finally, I would like to thank you all for taking the time to watch my presentation. I'd be more than happy to take any questions that you may have.